Theoretical physicists have had it all to do over the years. On one hand, there's the task of solving the enigma around objects and elements existing in quantum form. On the other hand, there's the pressure of outdoing Albert Einstein to disprove his theory of general relativity, or perhaps provide more evidence to support it. But what if there's a theory that can unite both concepts? Of course there is, and it's one that we're very familiar with. What exactly is this unifying theory called, and how does it unite some of the world's most widely referenced hypotheses? Let's find out. In simple terms, quantum physics is the theory of how everything works. This aspect of science specifically studies the behavior of matter and energy at molecular, atomic, and nuclear levels, as well as elements at microscopic levels. Back in the day, around the 20th century, scientists mapped out the laws governing the big objects, and they found that these laws are quite different from those that regulate the small objects and elements. Quantum itself is a Latin word meaning how much. But within the realm of science, quantum is used to define discrete units of matter and energy, as observed during quantum physics experiments. The popular belief amongst scientists is that Max Planck's scientific paper on black body radiation in the early 1900s led to the invention of quantum physics. Further development studies were conducted by other great scientists, such as Albert Einstein, Niels Bohr, Richard Feynman, Werner Heisenberg, Erwin Schrödinger, and even Max Planck himself. Interestingly, the concept of quantum physics tells us that objects can take different forms depending on whether or not they've been watched. As such, light waves sometimes act like particles, and particles also exist sometimes as waves. This phenomenon is called wave-particle duality. The wave-particle duality made huge headlines back in the day. In the year 1906, J.J. Thomson was awarded the Nobel Prize for defining electrons as particles. But just over 3 decades later, his son George won another Nobel Prize for proving that electrons are waves. So who was right and who was wrong? Well, it turned out both men were right, and the wave-particle duality would confirm this many years later. Also, scientists have discovered over the years that it is possible for matter to go from one spot to another without passing through the intervening space between them. This is called quantum tunneling. Interestingly, despite the supposed success of quantum physics, Albert Einstein had a few issues with the theory. Hence, he tried at different times to modify and even disprove it. Ironically, Planck didn't exactly fancy atoms or discrete bits of light. However, Einstein's work in 1905, when he published a scientific paper concerning a heuristic point of view toward the emission and transformation of light, Einstein envisioned light traveling at some sort of energy quanta rather than as a wave. Furthermore, Einstein suggested that energy in this form could be absorbed or generated as a whole, especially when an atom jumps between quantized vibration rates. With this new theory in place, Einstein offers new insights into the behavior of 9 phenomena in another scientific paper. The discovery in this paper also discussed the specific colors that Planck had initially talked about. In addition, Einstein's paper discussed how certain colors of light could eject electrons from metal surfaces in a process called the photoelectric effect. Consequently, Einstein put forward general relativity, which is more or less his own understanding of how gravity influences and affects the fabric of space-time. The theory was originally published in 1915 as a follow-up to his theory of special relativity that was published 10 years earlier. In the improved version, Albert Einstein posited that the space and time are inextricably connected, but ironically, there was barely any reference or mention of the existence of gravity. Einstein, who would spend the next 2 decades exploring the possibility of massive objects warping and twisting the fabric of space-time, a distortion process that manifests as gravity. In the end, the theory of general relativity relies heavily on gravity, which is the force of attraction that one object or element exerts on another. Critically, Sir Isaac Newton referenced gravity as one of his 3 fundamental laws of motion, otherwise known as principia. Expectedly, the gravitational pull or force that exists between 2 objects would most likely depend on the size of the objects and the distance between them. So, as the center of the Earth is pulling everyone on the planet towards it, even as the center of our mass is pulling back at the Earth, however, the Earth is barely affected by your pull, perhaps due to its enormous size. Meanwhile, the same force is responsible for keeping your feet on the ground. but the more massive body barely feels the tug from you, while your much smaller mass, you find yourself firmly rooted thanks to that same force. The great Albert Einstein posited in his theory of special relativity that the laws of physics are the constants for all static observers. In the same way, he showed that the momentum of light within a vacuum is also the same, regardless of the speed at which the observer is traveling. Subsequently, he posited that space and time were intertwined into a single continuum that's fondly called space-time. In other words, it means that events that happen at the same time for one observer could also occur at different times for another observer. After further research, Einstein found out and concluded that massive objects caused a distortion in space-time. Think of it as a large object dropped at the center of a trampoline. In this case, the proposed massive object would plunge down hard into the fabric, creating some sort of dimple. Once this is done, the marble spirals inward toward the body, being tugged in the same way that gravity of a planet pulls at rocks in space. Einstein's theory of general relativity has undoubtedly been one of the most reliable theories in physics over the years. However, it is unfortunately incompatible with the concept of quantum mechanics. So the fact that scientists recently made a breakthrough discovery during a lab experiment that could possibly unite both quantum physics and the theory of general relativity left the science world speechless. This new study, tagged quantum gravity, will be facilitated by our knowledge of wormholes and is expected to link both hypotheses seamlessly. However, since wormholes are hypothetical, scientists would need to create an artificial wormhole, and that's exactly what they did. According to reports, the research team behind the project built a hypothetical wormhole by using a computer wormhole model to run on a quantum processor. Thanks to this model, scientists were able to explore even further the physics of wormholes, as well as their potential connection to the proposed quantum gravity. Confirming the discovery, Maria Spiropoulou, the principal investigator at the U.S. Department of Energy office, said, "We found a quantum system that exhibits key properties of a gravitational wormhole, yet is sufficiently small to implement on today's quantum hardware. This work constitutes a step toward a larger program of testing quantum gravity physics using a quantum computer." Another scholar, Samantha Davis, a graduate student at Caltech, added that it took a really long time to arrive at the results. However, when they eventually arrived, it was worth the wait. In fact, scientists and astronomers were stunned by the outcome and the amount of detail it offered. From their observations, they discovered that wormhole-like behavior or traits can be explained from different perspectives, one through quantum physics and the other through general relativity. In continuation of her assessment, Spiropoulou emphasized that this new model doesn't exactly replace the current probes of quantum gravity. However, it offers a more sophisticated and powerful medium to study the concept of quantum gravity in the lab. And perhaps it could help us unite quantum physics and the theory of general relativity. But critically, this isn't the first time that scientists have explored this idea. Back in 2013, scientists achieved an outstanding feat by building a connection between wormholes and entanglement. Entanglement within the confines of quantum physics is defined as a scenario where two particles are able to link together in a certain way no matter how far apart they are in space. Consequently, physicists Juan Maldacena and Leonard Susskind successfully connected the concepts of general relativity and quantum physics when they proposed that wormholes were equivalent to entanglement, because both concepts help scientists to describe and prove the connections between distant areas in the universe. Spiropoulou described this idea as both a daring and poetic one, but somehow they were able to pull it off. Fast forward to 2017, when Daniel Jeffries, a physicist, looked into the theory more closely. This time, they designed a hypothesis where negative repulsion energy can help to keep a wormhole open for a substantial period of time, for insects and possibly humans to cross through it into an entirely different world from the past or future.